Good evening, everybody. I'm Anurag Gupta. I'm the TA for the course. Uh, so we'll wait for a few minutes before getting started. We'll wait for a few minutes. We'll maybe more people will join in, and then we'll get started with the session.
Yes, sir.
Okay, so it's 5:05. We'll get started. So my name is Anurag Gupta. I'm a PhD scholar at IIT Madras. I'm working in the neuromechanics lab, which is in the Department of Applied Mechanics. And the neuromechanics lab is headed by Dr. Vardhan SKM, who's also the instructor for this course. So we'll get started with the course. We'll get started with the live session. So this is how I planned the live sessions to be. There are about I have about 20 MCQ questions to discuss with you all. Uh, so I'll first read out the MCQ questions and then I'll give you guys 1 minute to respond. So you can just type out your answer in the chat box. So let me just share my screen. I hope I'm visible and audible. Can you let me know? You can just type whether you can hear me clearly here. Yes or no? Yes. Okay, it's audible. Okay. Yeah. So the I'll be discussing MCQ questions. Uh, okay. Mohan also. Mohana, I said yes. Okay. I'll be discussing MCQ questions with you all. And first, I'll read out the questions. Then I'll give you guys 1 minute to respond. And then I'll once I get your responses, I'll go in depth and discuss the MCQ question. Following which, I'll take questions from your side related to the MCQ questions. And then once we are through all the MCQ questions, uh, you can ask me general questions related to the week one's content, and I'll attempt to answer those questions. So let's start it. Okay, so the first MCQ question is this: a typical neuron has a resting membrane potential of about what? So we have four options here. One is minus 70 volts. Second is B 70 millivolts. C is 70 volts, and D is minus 70 millivolts. So you guys can just type out the answer in the chat box. I'll just set a timer. So this is I'll set a timer for 30 seconds. Just let me know what you think. Don't worry, it need not be correct. But whatever you feel, you can just uh, put the answer here. D. Okay. So two people, most of you are saying D. Okay. Okay. So I think that was a quick response. Most of you, I think you have seen the content, so you were able to respond quickly. Okay. Yeah. So D is the correct answer. So let's go through this review. Okay, so we are not dealing with voltages here in the sense we are dealing only with millivolts. So these two options are out of the question. So these two are wrong. So we have B and we have. Let me just erase this. So we have B and we have D. So like most of you all responded, the answer is D, which is minus 70 millivolts, which is correct because we know that the internal, we have, let's say this is the cell membrane, this is the ECF, and this is the ICF. So we take the voltage ICF minus ECF. So we know that the within the cell membrane, within the cell is more negative to what is outside the cell membrane, and hence the answer is 70 millivolts. You are right. Going on to the next question. What is largely responsible for the minus 70 millivolt resting membrane potential in a neuron? The first option is axonal insulation by Schwann cells. B. Opening of voltage gated sodium channels. C. The action potential. Or D. High conduction of K plus ions. So again, I'll set a timer for this time around 1 minute. You guys can get started. You can just give me a response, and then we'll discuss each and every option, why it is wrong or why an option is correct. You can take a guess. You uh, don't need to be cautious. Even if it is wrong, it is not a problem. Okay, we are done with our 1 minute. Okay, so some of you have responded B. Okay, B, B. Three of you have responded B. Okay, and one has responded D. Okay, okay, good. So you guys are responding. Yeah, so let's go through this step by step. We'll go through each of the options step by step. So the first option is axonal elation by Schwann cells. Uh, so Schwann cells are responsible for increasing the conduction velocity of the action potential. So they have nothing to do with what is the resting membrane potential. So that is not the option. So this is wrong. Okay. And then opening of voltage gated sodium channels. So when voltage gated sodium, so this is an action potential. Let us just assume that this is 0 millivolts. So this is in millivolts, and this is time. So we know that the action potential is at minus 70 millivolts. The resting membrane potential, sorry, the resting membrane potential is at minus 70 millivolts. And then the action potential uh, occurs when there is a stimulus and a threshold is reached. Okay. Uh, and once the threshold is reached, what happens is sodium gated voltage gated sodium channels open up. Okay. Once voltage gated sodium channels open up, there's a large influx of sodium ions, due to which the inside of the cell becomes positive, starts becoming more positive. So opening of voltage gated sodium channels actually causes an action potential. So again, this is not the correct answer. And option C is also not the correct answer, because I mean there's no link between resting membrane potential and action potential as such. Uh, and the fourth option is D, high conduction of K plus ions. This is the correct answer. So let us see why this is the correct answer. So there's something called as the chord conductance equation, which you would have gone through, which gives the value, which is used to calculate the value of the resting membrane potential. So let's say we have, so this is the chord conduction equation. Uh, so Gk plus, let me just write down the chord conduction equation. Gt Ek plus G Cl minus Gt ECl minus plus G uh, Ca2 plus by Gt ECa2 plus Gna plus by Gt into ENA plus, and so on for the other ions. So here GT is the total conductance. GT is the total conductance. Uh, Even before discussing that, let me discuss what is GK plus. So GK plus is the uh, conductance of the potassium ion across the cell membrane. So conductance is, resistance is uh, the amount of opposition. Similarly, conductance is how, with what ease will the ion move across the cell membrane. So this is the conductance of the potassium ion. Similarly, GCl is the conductance of Cl minus, and GCA2 plus is the conductance of calcium across the cell membrane. So GT is equal to GK plus GCl minus plus GCA2 plus, okay, and so on. So this is the overall conductance of all the ions combined. So now uh, let us discuss what is EK plus. So EK plus is the Nernst potential or the equilibrium potential of the potassium ion. So let me just create a new slide. Insert. Okay. So let us discuss what is this Nernst potential or equilibrium potential. So let us say we have this container which has a membrane, and there is we have potassium ions in large concentration here, and we have potassium ions in low concentration here. So that means there is a concentration gradient. So there is a concentration gradient across the membrane. Now let us say that this membrane is permeable to potassium. This membrane is permeable to potassium. Hence, the potassium ions will diffuse across the membrane because of the concentration gradient. Okay. Uh, but over time, what will happen is, since more positive charge is going here, uh, positive charge will start to accumulate uh, on this side of the membrane, and then there will come a time when due to this positive charge will oppose positive K plus ions from entering into the membrane. Even though there is still a concentration gradient, this potassium ion will not be able to enter, will not be able to cross the membrane. So that particular the voltage. So this particular voltage, due to this voltage, it won't be able to cross, and this voltage is called the equilibrium potential or the Nernst potential. Okay. Uh, so there is a Nernst potential based on the concentration across membrane. There is an equilibrium potential for all ions. So this is the Nernst potential or the equilibrium potential here. So this is the equilibrium potential for potassium ion. This is the equilibrium potential for chlorine ion, uh, and similarly for the other ions as well, sodium and calcium. So now at resting membrane potential, what happens is, at rest, the conductance of potassium is the highest. Okay, the conduction across the cell membrane of potassium is the highest. Hence, this particular ratio is the highest amongst all these ratios. Okay, hence the weight of this particular uh, Nernst potential is the highest. Hence, EM will be closer to the Nernst potential of EK plus, because the conduction of potassium is the highest, and we know that the The Nernst potential of K plus is, let me just check that. The Nernst potential of K plus is about, I think it is about minus 70. Can somebody confirm that? Since the Nernst potential is, so now basically what I'm trying to say is the equilibrium, the resting membrane potential will be closest to the Nernst potential of K plus, because the conduction of K plus is high at when there is no external stimulus that is being given. So this is the reason why high conduction of K plus ions is responsible for the resting membrane potential to be minus 70 millivolts. If, for example, the conduction of sodium ions was high, then the resting membrane potential would be closer to the Nernst potential of sodium ions. Okay, so this is the reasoning behind this. Uh, so before going on to the next question, if you guys have any questions related to this MCQ, you can ask me.
So
I
on
hope,
the internet,
yeah.
it is saying around 55 for sodium.
Okay, 50, 55 for sodium. Okay, but we are looking for potassium, right? The Nernst potential for potassium. So this is around minus 70 millivolts because the Nernst potential for potassium is negative, somewhere in the negative region. Let me just check.
Yes, sir,
Okay.
minus 90 it is saying.
Yeah. Okay. Yeah. So yeah. So you can see why the resting membrane potential is negative, because the conduction here is high, and then the weight attached to this Nernst potential, the Nernst potential of the K plus ion is high. So that is why the resting membrane potential is minus 70 millivolts. Okay. Uh, so if there are any other questions, I can take that related to this MCQ. If not, I'll go to the next MCQ. Okay. Okay, I'll go to the next MCQ. At the peak of the action potential, the membrane potential is A, exactly the Na plus equilibrium potential. B, close to but more positive than the sodium equilibrium potential. C, close but less positive than the Na equilibrium potential. Or D, exactly 0 millivolts. So you guys can answer this question. I'll give you guys 30 seconds to answer this. Let me put a timer for 30 seconds. Okay, I think I removed the question from the. Yeah, you can take a guess. So the recording for these sessions will also be shared with you all, uh, as well as the PPT and even whatever I've written, the notes here. So all this will be shared with you post the session. Okay. Okay. Let's see what is the response. Okay. B. Okay. C. A. C. B. Okay, so it's either C or B. That is most of the. Okay, and one has responded A. Okay, let's go through this. Uh, okay, so the first option is exactly the Na plus equilibrium potential, close to but more positive than the Na plus equilibrium potential, close to but less positive than the Na plus equilibrium potential, or exactly 0 millivolt. Okay, first let us eliminate the obvious wrong option, which is exactly 0 millivolts. So this is wrong. Now let us just draw an action potential here. So this is minus 70 millivolts, minus 55 millivolts is the threshold, and so when the stimulus is applied, an action potential, if the stimulus, if the graded potential reaches the threshold, then an action potential is generated, and then this happens. Okay, and this is 0 millivolts. Okay, so let us see what happens here. Let me take another color. So let us just assume that whatever I'm drawing with blue is the conductance of the sodium ion. Okay, so uh, this is just a crude diagram. I might not get the exact curve correctly, but you'll get an idea what I'm speaking about. So when the stimulus is applied, certain sodium ions start entering. So the stimulus can be either, for example, uh, uh, the stimulus can be, let's say, for example, a touch, and these can trigger uh, mechanically sensitive sodium channels, which then allow sodium ions to enter into the cell, and hence making the cell, the interior of the cell, more positive, and hence a small graded potential is developed. And if that graded potential reaches threshold, then what happens is voltage gated sodium channels open up. Okay. Uh, so when voltage gated sodium channels open up, the conductance of sodium increases, because now sodium ions are free to travel along its concentration gradient. So let us remember that uh, the concentration of Na plus in the ECF is very high, and if sodium gated channels, voltage gated sodium channels open up, then sodium will travel down its concentration gradient into the ICF, and this will cause a rapid depolarization. So depolarization is when it starts becoming, the interior of the cell starts becoming more positive, right? So so here let me draw the conductance graph of sodium. So it's initially very low, and then it suddenly shoots up after the threshold, and then it goes like this. Okay, so there is a brief window during which this sodium channels open up, voltage gated sodium channels open up, and then there is a rapid influx of sodium, and here you can see uh, after this the channels, the voltage gated sodium channel starts to close. We'll get into this later, uh, get into the mechanism later, but it starts to close, and then the contents of sodium starts to decrease. So this is the uh, conductance of Na plus. So when this starts to decrease, uh, no more sodium can come in. But at around this point, what happens is, let me take another color. What happens is potassium channels, voltage gated potassium channels starts to open up. Okay, and due to which there is an outflow of K plus. So if you recall, in the ICF, the concentration of K plus is high, and if voltage gated sodium channels open up, then K plus will start to move out, making the cell again, making the int of the cell more negative because positive charges are going out. So the internal ICF will start to become negative. So that means when the conductance of K plus across the membrane starts to increase, there is a rapid outflux of K plus ions, due to which repolarization happens. Okay, so this is just a quick overview. So when voltage gated sodium channels open up and the conductance of Na plus is high, what happens is, as we remember previously from the cord conductance equation as well, the potential across the membrane will try to go towards the Na plus equilibrium potential. Correct? That is the goal. If this the conductance, okay, so uh, that is the goal. It tries to go towards the Na plus equilibrium potential, and like someone pointed out, the Na plus's equilibrium potential is around 55 millivolts. So that is where it's going towards. But then you also see that the conduction of K plus increases, and hence repolarization starts to happen. So then it starts to decrease. So before it can keep on increasing towards 55, it starts to decrease. So around 40 millivolts is the peak. Okay, so it's close to but more positive than Na plus equilibrium potential. This is wrong. Exactly, the Na plus equilibrium potential is also wrong, because before that the potassium voltage gated potassium channels open up, and hence the conduction of potassium increases, and then repolarization starts. So these two are wrong, but the correct answer is close to but less positive than the Na plus equilibrium potential. Okay, so this is the explanation for this question. So if you guys have any doubts related to this, you can ask me. If not, I'll go to the next question. Okay, so some of you have joined in late. So for those who have joined in late, this is the format that we are following. Uh, I'm going to be discussing MCQ questions, and in the process of discussing these MCQ questions, we'll be going in depth in some of the concepts. Uh, and then once we are done with all the MCQ questions, I'll take general doubts related to week one's content. So the session is still about 6 o'clock. Uh, if you are able to complete it by 6, fine, or we can extend the session for some more time as well. Okay. So I hope this is clear. I'm going on to the next question. Let me just check if anybody has doubts. No. Okay. So the next question is, the sodium potassium pump is a type of facilitated diffusion and is active. B, a type of primary active transport. C, a type of facilitated diffusion and is passive. Or D, a type of secondary active transport. So I'll give you guys 30 seconds. You can write in your answer. Okay, we're done with the 30 seconds. Let's see what the answer is. B, A, B, B. Okay, B, A, B. 3 people have responded. Okay, 4 people have responded. B, B, A, B. Let's see. Okay, yeah, it's a type of primary active. So this is a straightforward this thing. It's a type of primary active transport. So there is energy involved in this. If you remember in the sodium potassium pump, there is energy involved, and there is 3 Na plus that goes outside the. So this is your cell membrane. So 3 Na plus from inside goes outside the cell membrane, and 2 2 K plus comes into this into the cell. Okay, so this is ECF, this is ICF, and because this is we know that Na plus concentration is high outside, so this is going against the concentration gradient. Similarly, there is K plus concentration is high inside, so the movement of K plus ions is against the concentration gradient. So energy is required to do this. So one question that I want to ask you guys is, why is this required? Why is this required? Why is the sodium potassium the why does the sodium potassium pump even exist? What is its role? You can just type out your answer. You can take a guess. So whoever has told B, that's the correct answer. So you can see here, I think in one of, so these are the slides. I'm trying to drag it. So you can see here there are a lot of things, options here. This slide basically covers everything, but we are only going to focus in this course on this particular type of transport, primary active transport, which is the sodium potassium pump. Okay, let's see for any responses. To maintain the concentration gradient so that Rm. Okay, Shashank, yeah, that's correct. Okay, so one of the main aims is to maintain the sodium, the concentration gradients across the cell membrane of sodium as well as K plus, because there are leaky potassium channels. Okay, and there is current, there is potassium ions that are leaking into the ECF. So we already know that the concentration of K plus is high inside and low outside. So K plus ions will start moving outside, will start leaking outside into the ECF along its concentration gradient through these leaky channels. Okay, and the aim of this sodium potassium ATPase, because of this leaky channel, the concentration gradient inside and outside can be affected, and hence the sodium potassium pump is used to maintain the concentration gradient. So I think, yeah, Shashank, you're right. uh, moving on to the next uh, Moving on to the next question, question 5. In the absolute refractory period, A, there cannot be another action potential because the sodium activation gate is open. B, there cannot be another action potential because the sodium inactivation gate is closed. Okay, so it's tricky here. You need to watch out. Uh, and C, there cannot be another action potential because the sodium inactivation gate is open. And D, there can be another action potential provided the amplitude of stimulus is large. So I'll give you guys 30 seconds again. You can answer this question. Be careful because it's slightly confusing here. Open, closed, activation, inactivation. This can be slightly confusing. Okay, so let's see what are the responses. B, D, B. Okay, 3 people have responded B, D, B. What about the others? Okay, I'll explain this now, this question now. B, D. Okay, so these are the two. Some people are good. There cannot be another action potential because the sodium inactivation gate is closed. And D, there can be another action potential provided the amplitude of stimulus is large. Okay. Okay, so we'll eliminate the first option. Uh, so in absolute refractory period, what you guys should remember is there are two refractory periods in the action potential. Okay, the two action potentials, two periods. One is the absolute refractory period. So this is the absolute refractory period, and this is the relative refractory period. Okay, relative refractory period. So during the absolute refractory period, no matter what stimulus is given, another action potential cannot be generated. Okay, and during the relative refractory period, there is possibility of generating the uh, uh, another action potential, provided the stimulus is large enough to. So you can see here that there is. Let us go to the terminologies. So this is called depolarization, when the membrane potential starts to become positive. Okay, then again when it starts to become negative, it is called repolarization, and if it goes below the resting membrane potential, that is called hyperpolarization. So in this case, you can see in the hyperpolarized state, what is happening is it is more negative, right? So the amount of stimulus that is required to actually reach the threshold is more. But in the relative, so this is the relative refractory period, and during this time, if we give a large enough stimulus, we can actually achieve another action potential. But in the absolute refractory period, no matter what we do, it is not possible to generate another action potential. This is because, like some people told, the sodium inactivation gate is closed. So let us recall how this works. So we have voltage gated sodium channel here. Okay, and this is in the rest state. Okay, so uh, this is the activation gate, and this is the inactivation gate. Okay, so what is going to happen is, uh, this is one state of the voltage. This is the voltage gated sodium channel. Okay, now what is going to happen is, once threshold is reached of minus 55 millivolts, upon when if a stimulus is large enough to make the membrane potential reach the minus 55 millivolt mark, then what happens is activation gets triggered, and it opens rapidly, whereas the inactivation gate starts to close slowly. Okay, and then there is a brief window where this is open, because this is closing slowly, and in that brief window, the conduction of sodium, uh, the sodium diffuses down its concentration gradient, large amounts of sodium ions, and then this depolarization happens, right? This is the cause. We already discussed this. We saw this. Why? So during this period, the conduction of sodium increases. I think somebody has joined. Okay, a few people have joined now. Uh, no issues. We'll continue. So, like I mentioned, uh, there's a large influx of sodium down its concentration gradient, which causes depolarization. But then after that, the inactivation gate is closed, right? Which is what causes this decrease. Uh, which is what causes this decrease in conduction of sodium, and only when. So let me just show what is the state now. Okay. Now what happens is, the inactivation gate is closed and the activation gate is opened. So it remains in this state until it repolarization happens, and the point resting membrane potential is reached. Then it again goes back to this state. So when the inactivation gate is closed, no matter what stimulus, even if threshold is reached, not reached, that does not matter. The inactivation gate is closed. No way to open it until the membrane repolarizes back to the resting membrane potential, and hence this is the correct answer. There cannot be another action potential because the sodium inactivation gate is closed. So whoever responded B as the option, that is correct. You understood it. Uh, so now let's go on to the next. Can I just show the slide pertaining to this? Let me check. Yeah, so this is what how it works. This is what I just explained. So there's an inactivation gate, there's an activation gate. The activation gate, when it is at resting membrane potential, it is closed. When threshold is reached, the activation gate rapidly opens and the inactivation gate starts to close. But there's a brief window during which the sodium diffuses down its concentration gradient, and then this is the state. Only when it gets repolarized does it go back to this state. Okay, so let's go down to the next question. If there are any questions related to this, you can ping. You can just type it out in the chat box. Okay. So the next question is: electrical impulses gather and accumulate in which part of a neuron in order to initiate an action potential? A. Dendrites. B. Axon hillock. C. Axon terminal branches. Or D. Nodes of Ranvier. So you can answer this. I'll give you guys 30 seconds again, as usual. So we are only reached sixth question. We have to discuss more 14 questions. Okay, let's see what are the responses. Okay, B, 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 everybody B. Okay, I'm glad you guys are interacting. Okay, Woodley also B. That's great. Axonal hillock, yes, you guys are right. So let us just open the slide where this is mentioned. So you can see this. I hope you can see the screen. So this is the anatomy of a neuron. So the first option is one of the options is nodes of Ranvier. That's not correct. That is the place where action potential is again caused. So uh, when the action potential is propagating, it is generated at the nodes of Ranvier. Uh, but what happens is, let me just. What happens is two things can happen. One is there is an action potential here. There is a graded stimulus that is applied here, and if it is applied continuously, for example, let me just see if I can write on this. Okay, so what is going to happen is, like Sir has already mentioned in his uh, in the lectures. Let's say there's an a stimulus that is applied here. Then another stimulus which is applied just immediately after this. If it keeps happening, what will happen is uh, there will be an influx of positive ions for sodium, and then this will reach the axon, and this keeps accumulating until threshold is reached and an action potential is generated. Or what can happen is, this is called temporal summation. Okay. Or what can happen is that different areas of the dendrite, here, you can get a stimulus at the same time, and this stimulus gets accumulated here. The positive ions get accumulated here, so they build upon each other like this. Then another one adds up. until threshold is reached and an action potential is generated. So this is called spatial summation. So yes, axon hillock B is the right answer. Okay, let's move on to the next. The opening of axon membrane. Okay, axon membrane. That is voltage gated potassium channels is responsible for which part of the action potential curve? Okay, so you guys can respond to this. Let's see what your response is. I'll give you guys 30 seconds. A is depolarization of the membrane. B is repolarization of the membrane. C is both regions of the curve, or D is none of the above. Okay, let's see the responses. B, 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 B. Okay, everybody seems to be agreeing with B. Let's see what. Repolarization of the membrane. Yes, that is correct. So we already discussed this. Uh, let's see. Yeah, so you can see here this graph. Uh, so at this point, voltage gated sodium channels open up, causing an influx. Causing an efflux of potassium, right? So positive charges start leaving the cell, and hence the cell starts to become more negative, which is what causes this downward repolarization. So that is correct. Repolarization is the correct answer. Now the next question: if action potential is initiated at the center of the axon, then the action potential propagates A towards the hillock, B towards the axon terminal, C both A and B, D either A or B. Okay, so this is an interesting conceptual question. Let's see what the answer is. Again, I'll wait for 30 seconds. You can think what the answer is. It's a very interesting question. So towards the end of the class, I will just name out a few important topics that are related to this. Actually, all the topics are important, but I'll just name one or two important topics that you should know definitely, and I'll also give a reference book which you can use for this particular week. Okay. Okay. So let's see what the response is. C C C C. Okay. One is A. C A C C C. Okay. Towards the Okay, so yeah, most of you have gotten it correct. It's C, both A and B. So what happens is, uh, what happens is, let's say this is your. Let me copy this. Okay, so what happens is, let's say you get an action potential, you get a stimulus here at the center, right? This causes an action potential. Then there is an influx of positive ions into the cell membrane, okay, into the axon, and this diffuses here as well as here, correct? Now since it diffuses in both the directions, the positive charges diffuse in both the directions. What happens is this area starts to get depolarized until threshold is reached. So then again an action potential is generated. Now what happens is once this action potential is generated, again there's an influx of Na plus, right? And Na plus diffuses here as well as back here. But let us remember that this area is in its refractory period. So in the refractory period, it cannot generate another action potential. So the action potential is generated here. It cannot be generated again here. Similarly for this, an action potential is generated here. So the answer is it moves, the action potential is moves towards the axon terminal as well as the hillock. So I think you got the concept right. The answer is both A as well as B. Okay. Moving on to the next question. At what membrane voltage do neuronal voltage gated sodium channels become activated? Okay. Let me just remove this neuronal term. So you can respond to this. This is a straightforward question. Let's see what the response is. B, 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 B. Okay. Yeah, I think you guys know this. It's very simple. It's just the answer is minus 55 millivolts. No need to discuss this. The hyperpolarization phase of the action potential is due to. Okay, so this is an interesting question. If you understood the conduction curves of the sodium and potassium, then you will understand this question. So you can respond. What is the answer? A. Opening of voltage gated chlorine channels, prolonged opening of voltage gated potassium channels, closure of resting uh, sodium channels, or closure of chlorine channels. So let's hear it. What is the answer? B, 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 B. Okay, I think you guys know the concepts well, which is why you are able to respond. Okay, so let us just look at. So here you can see that the what is that option? Prolonged opening of voltage gated potassium channels. Because there is prolonged opening of voltage gated potassium channels, you can see that the conduction here of potassium is still high. It does not dip as here it's like a spike for sodium conduction, but for potassium you can see it does not dip immediately. It's prolonged, right? So there's since it is open, it keeps on K plus keeps on traveling down its concentration gradient, causing this hyperpolarization. And then why does it go back to its normal resting membrane potential? Because there is the sodium potassium pump is doing its work continuously to maintain the concentration gradient. So after hyperpolarization, it goes back to its resting membrane potential because of course leaky currents, leakage potassium currents, as well as the work of the sodium potassium pump. Okay, so you guys are right. Going on to the next question. If the stimulation of a cell is strong, the strength of the action potential produced would be. So, okay, this is the 11th question. After this question, we'll take a break of 5 minutes and then we'll come back and we'll finish it in 15 minutes with the remaining questions. Okay. So, if the stimulation of a cell is strong, the strength of the action potential produced would be A. No different than that produced by weak stimulation. B. Weaker than that produced by weak stimulation. C. Stronger than that produced by weak stimulation. Twice than that produced by weak stimulation. Okay, so this question is slightly ambiguous. It's not properly worded. It could have been written in a better way. But okay, let's hear what your responses are. A. Okay. A. Three people have told A. Yeah, I think you got the concept. Uh, no different than that because it's okay. So what is not said in this question is this: weak stimulation as well as strong stimulation. In this case, we are assuming that the weak stimulation reaches the threshold. Okay, so we are speaking relative terms here. So let's say we have minus 55 millivolts is the threshold, and we have minus 70 millivolts is the resting membrane shell, and I have a stimulus here. So if the stimulus is going beyond this, like let's say here, or if it is even slightly below, just it just causes the potential to reach here. Whatever the cases, as long as it crosses the threshold, whatever the graded potential, the amplitude of the graded potential is, as long as it crosses the threshold, the action potential will be generated, and the action potential that is generated is the same always for that particular type of cell. Uh, so it's an all or none response, and the response is always the same. So this is an important property of the action potential that you should remember. Okay, so we'll just take a break for 5 minutes. We'll be back in 5 minutes, and we'll continue this discussion. So we have around 5, 6 more questions. Now we'll try to rush through some of the questions because we have already discussed some of the basic concepts. So I'll meet you guys back in 5 minutes. Okay, let's start. Resume the session. What just happened? I think there was some connection issue. That is why the meeting got disconnected. I hope you guys can hear me now. Can you guys hear me? Okay. Okay, let's resume the session. Accommodation happens because of A. Damage to myelin sheath. B. Membrane potential is maintained close to action potential. C. Membrane potential is maintained close to threshold. Or D. None of the above. So you guys can respond. What do you think the answer is? Okay, I'll wait for 15-20 seconds. C. Okay. Yeah, I think that is right. Membrane potential is maintained close to the threshold. So if you remember, the sir had talked something about hyperkalemia, where the outside concentration. So this is your cell membrane. This is your ECF. This is your ICF. If K, if the amount of K plus concentration increases by a slight amount, already the K plus concentration inside is high. But if the amount of K plus concentration increases by a slight amount, Then what happens? The resting membrane potential. So everything is linked. If you remember the what do you say, the Nernst equation. Uh, let's go here. So the Nernst equation, if you remember, so V equivalent equals minus RT by ZF ln Cin by Cout. So if the concentration changes here, Cin and Cout, if a particular ion, if it changes, then the Nernst potential or the equilibrium potential will change for that particular ion. So similarly here, if we change the concentration outside the cell, then this again affects the Nernst potential of this particular ion. And what happens is the concentration gradient decreases, right? Since the concentration gradient decreases, a lot of other factors come into play, and also the equilibrium potential also changes. So now, when the equilibrium potential changes, this affects the chord conductive equation. So, uh, if you remember, there's a chord conduction equation that we saw at the beginning. So this is the chord conduction equation, and you can see here that if this changes, then even EM will change. So what basically happens is, uh, so what happens is the membrane potential goes closer to threshold. Okay, goes closer to the resting membrane potential goes closer to the threshold. Now what this does is, uh, there is something called as accommodation that happens, due to which the the inactivation gate of the sodium channel is closed. Okay, because the resting membrane potential is close to the threshold for a sustained amount of time, this particular thing happens. And now, because this happens, it's in a refractory period, and action potential, no matter what stimulus you give, action potentials cannot be generated. So the answer is C, membrane potential close to the threshold. Then the 13th question: damage to Schwann cells produces more damaging and permanent effect than injury to oligodendrocytes. True or false? So you guys can answer this. Let's see what the answer is. Damage to Schwann cells produce more damaging and permanent effects than injury to oligodendrocytes. I'll wait for a few seconds and then we'll discuss the answer. Hello, is anybody there? True, okay. A, true, okay. Okay, so some of you have said A. Okay, let us discuss this. So if you recall Schwann cells, so we have glial cells, right? I think the spelling will be wrong, but we have glial cells, and then there are different kinds of glial cells. One is Schwann cell, another is oligodendrocytes. So we know that oligodendrocytes myelinate the axons in the central nervous system, whereas Schwann cells myelinate the axons in the peripheral nervous system. So we also saw that Schwann cells, the ratio, one Schwann cell myelinates one axon. Okay, whereas the oligodendrocytes, one oligodendrocytes myelinates 50 axons. So if one oligodendrocyte is uh, affected, then 50 the myelination of 50 uh, 50 axons is lost. So the damage caused is more if the oligodendrocytes are affected. So the answer this is false. Okay, because if one oligodendrocyte is affected, then it causes 50 axons to be demyelinated. And also let us look at what happens. So if oligodendrocytes are demyelinated, there's a syndrome called multiple sclerosis that happens. So, and if Schwann cells are affected, then the condition is called Guillain-Barré syndrome. So, if you recall, in Guillain-Barré syndrome, what happens is there is still chance of recovery. So, if myelination happens, it usually the effects start. There is weakness, slight weakness that starts at the leg, and then that reaches up uh, to the respiratory system, and they can also cause paralysis. However, if a person is put in a ventilator for a few days, then there is chance of recovery. Okay, there is a remyelination that can happen, and a person can recover from Guillain-Barré syndrome. However, if an oligodendrocyte is demyelinated, or if it is killed, then there's a cycle that happens: demyelination, demyelination, remyelination, demyelination. But there are only so many times the recovery can happen. After a certain amount of time, the demyelination happens at a greater rate than the rate at which remyelination happens. And also, after a certain amount of time, remyelination stops. And when this is reached, the first symptoms of this multiple sclerosis starts to appear, and by that time it's already too late for a recovery to happen. And the only thing that can be done is you have to manage the symptoms. Okay, so the answer is false. So this is the 13th question. Okay, so I have a few more questions to discuss, but we can also continue this in the next class. We have already exceeded our time by 20 minutes. Don't worry, we'll discuss all these questions in the next class as well. We'll continue this discussion. Uh, so I told you that I'll tell you a few important topics. So one of the important topics is the sodium potassium ATPase. That is a very important topic. Uh, so that is something that you need to know. And then we have the sodium weighted voltage channel. That is also another important topic. Then of course, action potential is a very important topic. Basically, all the topics are important, but you need to know the sodium potassium ATPase, voltage gated sodium channels, their functioning, uh, and then how the conduction during an action potential, the conduction of sodium and potassium changes, uh, and what causes this? What is Guillain-Barré syndrome, multiple sclerosis, hyperkalemia? So you need to know all these things. And the book that you can refer for this particular week is the first chapter of the book called by Linda Constanzo, Physiology by Linda Constanzo. Let me just show you the what the book looks like. So this is the book, Linda Costanzo, Physiology. So if you have any further doubts, you can refer to the first chapter of this book for only this particular week. Okay. Okay. So if you guys have any questions, you can ask me now, or we'll wrap up the session and we'll meet next week to discuss. We'll continue the session and we'll also discuss MCQs from week 2 in the next Saturday. So I hope this session was useful to you guys, and so you get an idea of how to solve these questions, how to approach solving these questions. So a lot of the answers are there in the videos itself. Okay, okay, guys. See you next week if there are no further questions. It was very nice to meet all of you. Okay, bye. Thank you, Mohana. Thank you, Aishwarya. Thank you, Sally. Thank you, guys, for joining in. Thank you, Mudli. Thank you, Swani. Swain. Shashmita Swain. Okay, bye. See you next week.